The role of fuzzy inference systems in modern cyber warfare, applications and implications. In the rapidly evolving landscape of cyber warfare, traditional binary logic systems increasingly prove inadequate for addressing the complex and ambiguous nature of modern cyber threats. Fuzzy inference systems, FIS, have emerged as a revolutionary tool in this domain, offering a more sophisticated and nuanced approach to threat detection, response mechanisms, and strategic decision-making in cyber operations. This comprehensive analysis explores how FIS is transforming cyber warfare capabilities and shaping the future of digital conflict. Understanding fuzzy inference systems in the cyber context. The foundation of fuzzy inference systems, based on fuzzy logic principles introduced by Lotfi-Zadeh, provides a mathematical framework specifically designed to handle uncertain and imprecise information. Unlike conventional Boolean logic, which operates strictly within true-false parameters, fuzzy logic enables systems to work with degrees of truth. This capability makes FIS particularly valuable in cyber warfare scenarios, where threats rarely present themselves in clear binary terms, but rather exist in complex, nuanced states. The operational framework of FIS in cyber warfare consists of three essential components: fuzzification, inference rules, and defuzzification. During the fuzzification process, the system converts precise input values, such as specific network traffic patterns or system behaviors, into fuzzy sets with associated membership functions. The inference engine then processes these fuzzy sets through predefined rules, and finally, the defuzzification stage transforms the fuzzy output into concrete, actionable decisions or responses. Applications in threat detection. Within the realm of cyber warfare, enhanced threat detection represents one of the most crucial applications of FIS. Traditional intrusion detection systems typically rely on rigid, predetermined rules that often fail to identify sophisticated attacks or generate excessive false positives. FIS introduces a more flexible and comprehensive approach by simultaneously evaluating multiple factors and analyzing their relationships through sophisticated fuzzy rules. For instance, when examining potential network intrusions, a FIS-based detection system simultaneously processes various data streams, including network traffic patterns, user behavior anomalies, and system resource utilization rates. Instead of simply triggering alerts based on fixed thresholds, the system evaluates the degree to which current activities match known attack patterns while considering numerous contextual factors. This sophisticated approach substantially reduces false positives while improving the system's ability to detect novel or sophisticated attack patterns. Adaptive response mechanisms. The implementation of FIS enables significantly more sophisticated and adaptive response mechanisms in cyber warfare operations. While traditional systems typically employ predetermined responses to specific threats, FIS can generate nuanced, context-aware responses based on multiple factors, including threat severity, certainty levels, available resources, and potential collateral damage implications. In a network attack scenario, a FIS-based defense system evaluates numerous factors simultaneously. The system assesses the confidence level of threat detection, analyzes the criticality of targeted assets, evaluates the potential impact of various defensive measures on legitimate operations, and considers the resource costs associated with different response options. This comprehensive evaluation enables the system to generate proportional and context-appropriate responses, ranging from enhanced monitoring protocols to complete system isolation, while minimizing disruption to legitimate network operations. Decision support in cyber operations. In strategic cyber warfare planning, FIS serves as an invaluable decision support tool for commanders and analysts. Modern cyber operations complexity, combined with the necessity for rapid decision-making, renders traditional analysis methods insufficient. FIS effectively processes vast amounts of information to provide strategic recommendations while accounting for various uncertainties and ambiguities inherent in cyber warfare. During cyber operation planning phases, FIS evaluates multiple strategic factors simultaneously. The system assesses success probabilities for various attack vectors, calculates potential collateral damage scenarios, evaluates resource requirements, analyzes detection and attribution risks, and considers possible enemy response patterns. This comprehensive analysis enables the system to provide commanders with detailed recommended courses of action, complete with associated confidence levels and risk assessments. Network Security Optimization (FIS) plays a fundamental role in optimizing network security configurations in real-time environments. Rather than depending on static security policies, FIS-based systems dynamically adjust security parameters based on current threat landscapes, system performance requirements, and operational needs. This dynamic optimization process involves continuous adjustment of firewall rules, access controls, encryption parameters, and security resource allocation, while maintaining optimal balance between security measures and system performance requirements. Attribution and source identification. The challenge of accurately attributing cyber attacks to their sources represents one of the most complex aspects of modern cyber warfare. FIS provides valuable assistance in this process by analyzing multiple indicators and evidence sources with varying reliability levels. The system combines technical indicators, behavioral patterns, and intelligence information to generate comprehensive attribution assessments with associated confidence levels. This capability proves particularly valuable because attribution in cyber warfare rarely achieves absolute certainty, allowing analysts to understand various attribution scenarios' likelihood and make informed decisions about appropriate response options. Challenges and limitations. Despite its significant advantages, implementing FIS in cyber warfare environments presents several substantial challenges. The complexity of defining effective fuzzy rules requires extensive expertise in both cybersecurity and fuzzy logic domains. These rules must comprehensively capture complex scenarios while remaining computationally feasible. Performance considerations also present significant challenges, as FIS operations can be computationally intensive, particularly when processing multiple input variables and complex rule sets in real-time response scenarios. The training and validation process for FIS-based systems requires extensive resources to ensure reliable performance under various conditions. Additionally, integrating FIS into existing cyber warfare infrastructure often necessitates significant modifications to current systems and operational processes. Future directions and possibilities. The future applications of FIS in cyber warfare show tremendous promise, with several emerging trends and possibilities. The integration of machine learning algorithms with FIS could enable more adaptive and sophisticated systems capable of learning from experience and improving performance over time. Advanced algorithms may eventually facilitate automated generation and optimization of fuzzy rules, reducing reliance on human expertise while improving system adaptability. The development of distributed FIS architectures could enhance scalability and resilience while enabling more sophisticated cooperative defense mechanisms. Improved visualization techniques for fuzzy systems would assist analysts in better understanding system decisions and optimizing performance parameters. Conclusion: fuzzy inference systems represent a crucial advancement in modern cyber warfare capabilities, offering sophisticated tools for threat detection, response coordination, and strategic decision support. While implementation challenges exist, the ability of FIS to handle uncertainty and complexity makes these systems increasingly valuable in the evolving cyber battlefield. As cyber threats continue growing in sophistication, the role of FIS in cyber warfare will likely expand significantly. Future developments in this field, particularly when combined with other advanced technologies, promise to enhance our ability to defend against and respond to cyber threats while effectively managing the inherent uncertainties of cyber warfare operations. The successful implementation and continued development of FIS in cyber warfare requires ongoing research, development efforts, and collaboration between experts in fuzzy logic, cybersecurity, and military operations. As these systems continue to mature and evolve, they will become increasingly integral to effective cyber warfare operations and defense strategies, shaping the future of digital conflict resolution and cybersecurity practices.